Okay, this is Dr. Miller, and I will be going over how to answer the questions for pre-lab 4.1. This pre-lab is due November 4th, Thursday at 4:30 p.m. We will be doing the lab the following week. So the chemical reaction you will study in this lab activity is shown in reaction 4, which shows us sodium hydrogen carbonate in a solid form plus acetic acid that's been not totally pure, it's aqueous solution, and it gives us sodium acetate in aqueous phase, plus water is formed and CO2. So what is coming up apart here is the sodium is breaking apart from the hydrogen carbonate. This is also known as sodium bicarbonate. Either name works. So the sodium comes apart and forms with the acetic acid. The acetic acid loses its proton here, and the sodium replaces it as far as aqueous solution. Those are really spectators, but we'll consider that they're dissolved together. And so then that has the carbonate breaks apart. So we have the hydrogen from here and the hydrogen from there, and one of the oxygens comes apart to form water. So we have a liquid water. What's left over is the carbonate, losing the oxygen to form carbon dioxide gas. So when we see a solid and an aqueous solution and then aqueous products, water as a product and gas as a product, you can say what you think you will observe as this reaction takes place. What will you see in the reaction vessel? So the maximum volume in the syringe used in this activity is 60 milliliters. We know that that's going to be, we're going to collect the gas. Very similar to the first wet lab we did where we collected gas, carbon dioxide, when we broke apart in water. Alka-Seltzer. Alka-Seltzer has a lot of hydrogen or has sodium hydrogen carbonate in it. So this is a similar reaction to what we used then. Instead of water, we're using acetic acid. And so we're going to have gas formed. We collect it in a graduated cylinder in that lab. At this lab, we're going to collect it in a large plastic syringe. And the most that the syringe can collect is 60 milliliters that we can measure. So we don't want to collect more than 60 milliliters. So we're going to calculate using the ideal gas law at STP, standard temperature and pressure, calculate the mass of sodium bicarbonate that will react with an excess of acetic acid to produce 60 milliliters of CO2, carbon dioxide. Now, how I remember STP values is it's a cold day at the beach, because at the sea level, atmospheric pressure is 1 atm. So we're at the beach, we're at sea level, and it's cold because it's only 0 degrees Celsius, and we know we can convert 0 degrees Celsius to Kelvin by adding Celsius and 273 to get the Kelvin. So it's 273 Kelvin. So that's how I remember a cold day at the beach. So we're making this at the cold day at the beach. We know room temperature is going to be a little bit different, but we're going to calculate it as if we are at sea level and at only 0 degrees Celsius, which is, as we know, 32 degrees Fahrenheit, so it is cold. So we need to look at the balanced chemical reaction. So we look at sodium hydrogen carbonate or sodium bicarbonate. We see that there's an implied 1 in front of it, so that 1 mole gives us how many moles of carbon dioxide? 1 mole of carbon dioxide. So we know it's a 1-to-1 ratio. So for whatever moles of sodium bicarbonate we have, we'll get 1 mole of carbon dioxide. So what we need to figure out is how many moles of carbon dioxide we will have at 60 milliliters at these conditions. So let's use the ideal gas law, which we need to remember as being PV equals nRT. Now, we need to find the mass of sodium carbonate, but nowhere in here is a mass. This is pressure, this is volume, this is number of moles, this is the gas constant, and this is temperature. So we get to mass by going through moles. So we're going to figure out how many moles 60 milliliters of CO2 is. So the pressure is 1. So that's given to us in STP. So P equals 1 atmosphere. Our volume equals 60 milliliters, but whoops, we know from PV equals nRT that these have to be in certain units, and volume has to be in liters, right? So we need to convert the milliliters to liters. So 1,000 milliliters in 1 liter. So we'll convert that to feed into our equation. N is our unknown. The gas constant we're going to use is N is unknown. The gas constant is 0.08206, and T, temperature, is got to be in Kelvin. It's got to be in the absolute temperature scale, and it's told to us that it's 273 Kelvin. So you need to plug these values in and solve for our unknown number of moles of CO2. Then, because we'll find, eventually we'll have, find moles of CO2, because we're converting 60 milliliters to moles under these conditions, and we know that for every mole of CO2 we need 1 mole of sodium hydrogen carbonate. So then we'll know how many moles we have, and then we'll use the 1 mole of sodium hydrogen carbonate and what the mass of that is, how many grams in 1 mole. So we go to the periodic table and we add the sodium and hydrogen and 1 carbon and 3 times the molar mass of oxygen to get our molar mass of our sodium bicarbonate, and we'll put that in there. So we'll multiply whatever our moles of this is, which is unknown, times 1 divided by 1 times our molar mass of sodium hydrogen carbonate, and that'll answer number 2. Then going to number 3, it says, okay, if that's the amount of mass that you're going to use to get 60 milliliters, and 60 milliliters is as big as our syringe is, we want to choose 5 different masses that's less than that. So just write down what masses would be that you could measure that are less than that. Okay, so that's the first page. So we'll flip it over. Oh, the second page, but you know what? I'm going to stop it now because we don't want to load too much up. So this is about 8 minutes.